The hadronic theory says that protons are also shock accelerated in the dissipation region and may interact with photons of the gamma radiation. So now remember, we talked about this earlier in my thesis. Remember how if you actually interacted, if you had protons that interact with highly excited photons, remember what happened? You would basically produce some intermediate excited particles, which then basically leads to making neutrinos later on. So this is the theory in which neutrinos will ultimately come out of gamma ray bursts. So let's read through this. The hadronic theory says that the protons are also shock accelerated in the dissipation region and may interact with photons of the gamma radiation to produce pions. So pions are intermediate particles. They're unstable. They will not just stay as pions. They will become more stable particles. The hadronic picture allows for the production. The hadronic picture allows for the production of neutrinos and is supported by Waxman-Baukol. So the two authors here that we're citing are Waxman, Elie Waxman. Hopefully he's okay. Baukol, B-A-H-C-A-L-L. Waxman is W-A-X-M-A-N. Baukol is B-A-H-C-A-L-L. I think Waxman is still my LinkedIn friend, so hopefully he's doing all right. And Baukol, I think, is a more senior guy. The photon meson interaction resulting in the intermediate delta plus of mass 1232 MeV is thought to dominate neutrino production in the work of Waxman Baukol. So let me show you. Basically, this is saying a proton plus a photon will give us something called a delta plus. This is a very unstable intermediate particle of mass 1232 MeV, which will then give us neutrons and pions, or protons and pions. If it's a neutron and a pion, then it's a neutron and a pion plus. If it's a proton and a pion, then that pion will be a neutral pion. And then depending on, basically these pions are unstable and they will decay into muons and neutrinos, or electron, positron, and neutrinos. Or even if it's a neutral pion, it will decay into gamma rays. A perfect example of the difference between a bachelor's in physics and PhD in physics. Love your passion for it. Oh, thank you, Einstein. And Erwin Schrödinger would be proud. Oh, thank you so much. Thank you, thank you. So basically, you have seen this interaction already. If you saw my previous live, let me show you. This is what I'm talking about. That right there. Basically, a proton and a photon. And remember, we already have gamma rays in this environment. We know, we have proof of that because the whole thing started by getting gamma rays from gamma ray bursts. Basically make an intermediate particle called a delta plus particle, which has mass of 1232 MeV. This is very unstable. This is an intermediate particle. It's not going to stay as a delta plus. It's not going to hang out as a delta plus for very long. It will decay to make either a neutron as in the stuff that we know and love, neutron and a pion plus, or a proton and a neutral pion. If it's a pion plus, then that pion plus will give us a muon and a muon neutrino, and the muon plus will decay further into a positron, an electron neutrino, a muon antineutrino, and a muon neutrino, all regular stuff. You can look up how a pion decays and you'll get this sort of equation. You can look up how a muon decays and you'll get this sort of equation. If muons didn't decay, we would have more muons, right? But muons decay, and that's why we have electrons. They decay into electrons or positrons, depending on which one. And then, of course, we get more electrons. And then the pion plus, because you could have also made a pion plus, remember, as an option, and then that would decay into gamma rays. So either way, in this interaction, at the end, you have neutrinos, potentially, and more gamma rays. Now, we already had gamma rays, so we're not so interested in seeing more gamma rays, but potentially, through this hadronic acceleration, you could get neutrinos. Reese! Hi, Reese. Hello, everybody. Thank you so much for joining. Welcome to the live. Thank you, Crazy Sick Wine. Thank you, Reese. Happy New Year. So basically, the leptonic theory